Hey guys, welcome to another lesson, and today we're looking at the electric field strength, right? So we did Coulomb's law, our last lesson, and we've learned that charges have electric fields, right? And if intertwined can produce a force, right? Now, we have, so each electric field has its own force, right? So that's known as your electric field strength, right? So electric field strength is the force acting per unit charge at a point in the field, right? So if we take a charge, a positive charge here, right? So electric fields are moving, pushing forces away from the charge, right? Now if we take this point here, right? So what it is this point in our electric field is our electric field strength is the force that's acting on this little charge right there, right? So once you have a charge inside another electric field, the force that it feels is actually known as the electric field strength, right? So, and it has to be in that the field lines, right? Once it goes outside of field lines, then there is no electric field strength there because the force is not felt beyond that point, right? So for a charge, just a single charge, the electric field strength is the force over the Q, right? Or the Q here means our charge, right? And or it's equal to the charge divided by 4 pi epsilon r squared, right? Now epsilon is known as the permittivity, right? And permittivity tells us how well a charge, or well something can actually store charges, right? So it's how well a medium store charges. So that's what permittivity is, right? So we normally use the permittivity of air or free space, that some books will have it, right? And you'll see it noted as epsilon naught, right? So the permittivity, which is free space for some books, which is basically just air, is 8.85 times 10 to the negative 12 Coulomb seconds per Newton meter squared, right? So that value is a constant, right? And we will come across this later, that K is epsilon over epsilon naught, right? And we will look at this further, but you can actually note that for future reference, right? So if you're given K and if the medium is not air, then you can find epsilon of that specific material, right? So let's look at the electric field within a parallel plate, right? So a parallel plate means we have two metals, right? We charge one with a positive charge and the next with a negative charge. So because there are two opposite charges, remember two different charges we'll call an attractive force. So we have the field lines moving between the two plates, right? And we notice it's moving from the positive to the negative because positive charges have their field lines going away from the charge, right? So the direction of the arrows are very important. So it moves from positive towards the negative, right? So in this region that we have the field lines, there is the electric field strength, right? So therefore we can find the electric field strength at any point because this here is a uniform field, right? So at any point in this field, so we can have point A here or point B right here or C or D at any point within the two plates, the electric field strength is the V, and this V means the voltage difference between these two charges, right? So the voltage difference between these two charges over the distance between the charges, the charge plates, right? So the voltage would mean that this positive plate will have, so basically these plates will be connected to an external battery source, right? So it's connected to an external battery source. So therefore this plate will have a different charge amount than this plate. So the difference in those charges will be your voltage, and we divide by the distance of the plates, right, to give us the electric field strength. So we should note something, that if we extend the distance between the plates, right, then the force, the electric field strength, will be less, right? Because now we're creating an area where we no longer will actually be inside the electric field strength, right? So remember, these lines only extend to so much and no more, right? So the further you're getting away from it, right, then you're having the tendency of not getting a high force. Now, if we're supposed to reduce that distance to make it smaller, then all we're doing is increasing that force, right? So we're increasing the space for the charge. Well, you're decreasing the space for the charge, right? So you will increase the electric field strength being felt anywhere within that space, right? Now, if we have the plates again in these two cases, but this time we're using a single charge, which is your electron, right? So we know an electron has a negative charge, right? So putting an electron within a parallel plate, right, it will be attracted, it goes with the flow, right? So it will be attracted to the positive side because it's a negative charge, it's going to be attracted to the positive, right? But what if when we put the electrons there, we're actually pushing it to the positive side, right? So what we're actually doing is giving the electrons work, right? Because in a normal state, the electrons will generally just move to the positive, right? But we're actually pushing it to go faster, right? So we give electrons work, right? In this case. So that's how, so this work would be less, right? Because it's going with the flow, right? So you just need a little push and it pushes faster, right? But let's look at the second one, right? So now we want it to go to the negative side, but the negative side is repelling that electron, right? So we have to push more for that electron to be sent to your negative plate, right? So now we're actually doing work against the electric field because the electric field is actually saying, hey, you should be going that way, but we want it to go that way. So we're going against the electric field, right? Because this is a negative charge and we're going to the negative plate, right? So in this case, the energy that is being lost or being stored will be stored as the electric potential energy inside your charge, right? Because we're actually going against the repulsive force, right? Now, the electric potential, right, is, as we looked here in this V, so electric potential is the difference between the charge concentration at one point to that of the next point within a range, right? So if we have, if we have a material that has its charge on one side and charge on the next, right? So the potential difference is the difference between the charge amount here and the charge amount there, right? So the electric potential tells us, and it also tells us, because there's a difference in charge, it works something like osmosis or diffusion, where it's high, it moves to where it is low, right? So that's the same thing with charges. Where it is high, it actually has energy to move to where it is low, right? And that's what electric potential is. So electric potential is the work over the charge, the quantity of charge, right? Or if it's for just one single charge, then the electric potential is K, which is the K right here, equal, so K times the charge, the quantity for the charge, over R. Now, R represents the radius of that charge, right? So remember, a charge is just a point charge that you see, right? So the radius would be, since it's a circle, right? So it's the radius of that little point charge. Or we can eliminate the K and we get Q over 4 pi epsilon R. And remember, epsilon, once it's here for free space, is 8.85 times 10 to the negative 12 coulomb seconds per meters squared Newton. All right. So that's it for electric field strength, right? And for next class, we'll be looking at using these equations to actually help us to calculate some unknown quantities. All right, so thank you very much, guys, for watching today, and see you guys next time.